Welcome to radar engineering course. We continue here a radar equation. Now we have seen in last lecture that what will the range required, how much will be the maximum range and minimum range that we have seen, and then for a given particular device, so how to obtain the range that we have seen. But there are some ambiguities to identify that what will be the range for the radar. To avoid it, so we need to use a device in such a way that will generate a pulses with a different frequency or a different width. Okay, or in between the two pulses there will be large gap, or that train of pulses is to be set. Okay, so now we go further now. So what is the radar equation? So radar equation just define that what will be the power transmitted we require, and what will be the minimum detectable signal we are supposed to be expecting here. Okay, so now this one we supposed to consider here, and we just talk about what will be the minimum detectable signal required, okay, for a given particular range. So that minimum detectable signal is depending upon that what will be the transmitted power that is transmitted by the radar, and what will be the range of the object. Okay, it means what is the distance of the object from the radar there. So this that's why we need to know about that what will be the first transmitted power of the source here, or a radar here. So to understand that a radar range equations, we supposed to consider that a given particular antenna will radiating the signal there. Okay. So in that case, so what will be the required? Okay. So what will be the requirement here? So that is to be seen here. Okay. So right now we just consider here. So how much is the requirement? Okay, for this particular power, what will be the distance, everything that we'll see here. So now when we supposed to consider that power transmitted by the radar, so in that case we supposed to know that what will be your antenna, what type of an antenna we have, what will be the gain of this particular antenna. Okay, then what will be the effective aperture area of the antenna. So based on that, what will be the power transmitted by the antenna that will be higher or a maximum. So we need to consider that what will be the gain of an antenna and the effective aperture area of an antenna, so that we will get that power will be radiated in all the directions. Okay, so this way I draw here, or we will get the a narrow beam this way. So we need to think over here. So whether our antenna will give us a broad beam width or larger area, or whether our antenna will provide a narrow beam. Okay, but the area will be small here in that particular case. Now, so if we fix our radar in a given particular direction, so then there will be the narrow beam. But nowadays the devices are available in that case that radar is transmitting signal in all the directions. Okay, radar transmitting the signal in all the directions. So that's why we know need to consider that what will be the requirement here for the antenna. Our aim is about to get the exactly the signal to be transmitted in a given direction. Okay, so that distance covered by the particular signal or distance reached to the given particular distance is to be a large, so that we will be able to detect the signal from the object even if it will be a far away from the our source there. So we see here, so what will be the power? transmitted power. So then for a transmitted power, we supposed to consider that a isotropic antenna, it radiates a power in all the directions. But here we can consider that our antenna radiate in only one direction. But to understand that a gain and effective aperture area, the equation of a radar, so we supposed to consider that a power radiated by an antenna uniformly in all the directions. So in that case, so if supposed to be your antenna is there, so it will radiate the signal in all the directions. So that's why we can say that uniform radiation. Okay, uniform radiation by the your antenna there. Okay, so we supposed to know about that what will be the antenna, so it radiate the power in uniformly in all the directions. That's why we supposed to consider the isotropic radiator or a isotropic antenna. Then it radiate in all the directions, so that's why it is just like if you see the surface, it will be nothing but a, that is about, it looks like a sphere or imaginary sphere, and that imaginary sphere of a radius r. So in that case, we supposed to consider that a transmitted power, okay, that by the given antenna, okay, that is about isotropic antenna with a imaginary sphere of a radius r here. This is about a r is the imaginary sphere of a radius. So from this transmitted power, we supposed to find out that a power density, okay, power density at a distance r, okay, this is about at a distance r, power from this antenna, power density at a distance r from the radar, okay, that is about our device here, power density at the distance r, so that is nothing but a distance, okay, here we supposed to consider that a power density at this particular point from the source, so it is transmitting here. So that's why we can write here, we can write a power density, okay, this is about a power density by a isotropic radiator or isotropic antenna at a distance r here. So it will be is equal to what? A pt by 4 pi r square. Okay. So now we supposed to consider that the antenna is to be radiated here in all directions. But our aim is about that antenna is to be radiate the signal only in a one direction or only in a given direction. Okay. So in that case, we should know that that antenna is to be highly directional. Okay. Or we supposed to consider that that antenna is providing a narrow beam. So this way, instead of a broader beam, so we supposed to get the a narrow beam of narrow beam antenna. So in that case, so narrow beam antenna, so density we supposed to consider at that particular point. Okay, in a we'll get that power density at a particular direction only. Okay, that is about our aim. And then we say that only in a given direction. So that's why the whichever antenna we are supposed to be using here, so we are able to measure the gain of an antenna. So gain of an antenna, it is nothing but what? What will be the power density radiated in a given particular direction to the power density in a isotropic radiator. Or we can consider that with the same transmitted power, what is the PT, so it will radiate in all the directions. And this one is about a radiated power only in a given direction. So that's why we can find out the gain of an antenna. So gain of a given antenna or a your device here. So we can consider that gain is equal to what? What will be the maximum power density radiated by a directive antenna here. Okay, so this one we can consider that suppose we have a directional antenna, so we supposed to find out the gain, that is a maximum power density by a directive antenna Okay, because we have a highly directional antenna. Divide by, okay, divide by same. We can consider that a power density radiated, power density radiated by a lossless isotropic antenna. Now for this particular thing, the condition is here. So whichever the power density we are getting by the direct to antenna and a power density radiated by this loss isotropic antenna, the condition is only a single or a simple here. So in this case, the condition will be what? We supposed to consider that the input power given to the and both the antenna will be the same. Okay, whatever the input power we supposed to use, what will be the transmitted power for both the antenna is to be the same. So in that case, we find out that a power density of this antenna. Now, power density by the isotropic radiator. So instead of that, if we supposed to find out the power density by, okay, so power density by a antenna which are the signal radiated in a given direction. Okay, only in a one direction. So in that case, we find out for a given particular antenna, so power density, okay, we can find out a power density at a distance or a range, okay, at a distance or a range r, okay, from what? From what? From the directive antenna or a directional antenna. Okay, from a directional antenna or a directive antenna. So this is nothing but what? Again, a given particular direction. Okay, so in a given particular direction, that power is to be irradiated. Okay, so we supposed to consider that a whatever the power radiated by the given particular antenna, okay, so that is to be obtained. So this one we can find out what will be the power transmitted, what will be the gain of a given particular antenna, and the 4 pi r square. Okay, that is about it for a spare. For a spare, it will be a 4 pi here, and that range will be a r square. Then this is about a from a given particular antenna, your signal is transmitted. Okay, so means what? We have a radar transmitting the signal to what? To the object. Okay, now this one is about our object. So radar transmitting the signal to the object. Okay, this is at a given particular range. Then we are supposed to find out that what will be the power radiated back to the radar here. Means that is nothing but a echo. We're supposed to consider that when a radar transmitting the signal, okay, so then it radiates the signal in a space. When that object, that signal will reach to the given particular object, then that object re-radiate that particular signal. Okay, and that signal is nothing but what? A reflecting signal, or we can say that a echo signal. So that is nothing but a re-radiated signal. So that's why we're supposed to find out what will be the re-radiated power density. Okay, back. Okay, power density, re-radiated power density radiated back to the a radar. So that power density back to the radar, it is depending upon that what will be the a target cross section, what will be the radar cross section, okay, or which simply we supposed to say that what will be the a cross section. So in that particular case, we should know here, okay, it's supposed to be here. So we supposed to consider that what will be the cross section of the a device there. So radar cross section, that is nothing but what? that is defined by the what will be the power re-radiated or returned to the particular direction or to a given particular direction there. Okay, so means this is about incident power, this is about a reflected power or a echo signal. Okay, so that's why we supposed to find out a re-radiated power density. This is about nothing but what? A power density that is from the range R here. So we supposed to find out that a power density from the re-radiated one. Okay, echo signal now. So in that case, we find out a re-radiated power density. Okay, re-radiated power density back. Okay, that is reflected. We are supposed to consider that back at radar. So what will be that power density? Okay, so we supposed to consider that just re-radiated power density back at radar is equal to, that is, what will be the transmitted power, that is about a radiated power PTGT. This is for the gain, transmitting gain of an antenna. So that's why you can say that GT here. So 4 pi r square, and then depending upon that a cross section. Okay, so that is about a sigma here. So sigma generally we supposed to consider that a what will be the radar cross section or area. Okay, radar cross section or a area observed from the object. Okay, so that is nothing but what? For a 4 pi r square. This r is nothing but what? Here we supposed to consider that radar is about your incident signal. Here is the object. This is about our object here. And then this particular portion is about what? This particular portion is about what? From the radar. Okay, this is about a particular portion. It is from the radar. And this particular portion, it is from what? From the object. Now this is about a for this object. It is a reflecting one. This is about a echo signal. For the echo signal. So we supposed to find out that a radar cross section of the target. Okay, radar cross section of the target. Okay, so that's why what we supposed to consider here is sigma by 4 pi r square, that is from the given particular, okay, from this particular object. It will reflect the power. So that's why a power density from the radar cross section. Okay, power density from the radar cross section that is returned, or we can say that returned to the radar. So we can find out a re-radiated power here. So this is about a re-radiated power. So then at a radar there is an antenna. Okay, there is an antenna at a radar. There is an antenna. So antenna will receive the, now this signal reach at this particular place. Okay, this is about a signal reach at this particular. Then here is a radar, and for this radar there is a antenna. So that antenna will receive the signal. Okay, so antenna receive the signal means whatever the antenna is present in the radar, that antenna captures whatever the incoming signal or signal reflected from the object, that will be accepted by or captured by this antenna there. So that depending upon that, what will be the area of an antenna? Area means what? Effective area of an antenna. So that is about a effective area. So radar, at a radar there is a receiving antenna that will capture whichever the power density radiated by this object or echo signal by this object. So that is to be defined by a power received or a received signal at a particular at a radar here. So it is nothing but what? This is about your transmitting signal or power density here from this isotropic antenna. We supposed to consider it is a directional one. That's why gain. Okay, and then a sigma, that is about a echo here. Okay, echo signal radiated by this object, and then what will be the effective area of a antenna here? Or we can say that we can find out that a effective area of the receiving antenna is A, effective area of this receiving antenna. It is depending upon that what will be the physical area. Okay, what will be the physical area and the aperture efficiency. So we supposed to consider that physical area and the aperture efficiency. This is nothing but a antenna aperture efficiency, and this is nothing but a physical area. And this, that's why we will get that effective area. Aperture efficiency, physical area means we have a large dimension of an antenna, but which dimension effectively accept or capture the signal. So that's why we supposed to find out that effective area. Okay, effective area. So whichever the power received can be calculated here with respect to a transmitted power, whatever the radar cross section. Okay, then we can say that a effective area term. So using this, we will find out. Okay, using this particular equation, we say that Pt, we have a G, we have a sigma here. This one is about a 4 pi term. It is twice here. R raised to 4 here. This is about a received power. So this is about R is nothing but what? A range. And from this, what will be the maximum range by the radar? Okay, so what will be the maximum range of a radar? So that can be calculated. That is, we can say that R is nothing but the range of a radar. So that's why we can say that maximum range R max is equal to what? Whatever the PT. This one we will not say here right now, GT. No need to see. We will not talk about that different antenna because antenna is same for the transmitting and receiving. Okay. So we will have a effective area here. So I think forgot here. Okay. So effective area. Then your cross section here. Okay. So this one. Okay. This one is about a cross section of an antenna, and we have this 4 pi. This one 4 pi square here, and this one we have this power received. So now instead of using the term a power received, okay, so we can consider that a minimum detectable signal, or we can say that whichever the signal received at the given particular point raised to 1 by 4 here. This one, okay, so this one is about a raised to 1 by 4. Okay, so this one is about a R max. So R max is depending upon that what will be the minimum power received by that antenna there. Now here a radar range equation will tell you what will be the maximum range. Maximum range depending upon that what will be the minimum signal received by the a device. Okay, so that this way we can find out that a maximum range of the a radar here. That is about a R. So this one depending upon that what will be the antenna we are using, what will be the gain of an antenna. Then again we have the effective aperture area of an antenna. Okay, this is about a gain of an antenna, effective area or a aperture area of an antenna. Okay, so with this we will calculate that what will be the R max. Now the gain G is term is useful for the transmitting antenna. So effective area, this is for the receiving antenna. So we can write AE with respect to the gain of an antenna here. Okay. So we'll rewrite the again a equation here, that is about maximum area. Okay. We will consider here. So this one we consider right now again. We'll write again R max. That is about a R max here. A is nothing but what? What will be the transmitted power? What will be the gain? What will be the effective area? What will be the cross section here? And 4 pi bracket square. And this is about a minimum detectable signal raised to 1 by 4. This is about your R max. So then we can write effectively what will be the exactly at a given particular transmitted power, what will be the minimum detectable signal here. Okay, so this one we can consider. So we can write in another way also, because a transmitting and receiving antenna both are same. So that's why we can consider that effective area of an antenna, that is A, can be write in terms of a gain of an antenna. So generally gain of an antenna is nothing but what? A 4 pi effective area divided by a lambda square. This A is nothing but what? If aperture efficiency. Okay, antenna aperture efficiency is about rho A. This is A here divided by a lambda square. Okay, so then we consider that a lambda is nothing but what? What will be the frequency? Okay, so we are using, that is wavelength. Okay, but we supposed to talk about that radar is used at a given particular frequency. So we supposed to consider that if what is the frequency range of a given particular radar there, operating range of the radar here. So if we put that either in terms of a G here, or we can write A here, so we'll get the two equation either in the form of a G or in the form of a here. So I'll write the equation R max is equal to what? PT here, then G square is about lambda square sigma by 4 pi. We have one we supposed to consider here, it is about a cube now, and a S minimum. Or okay, again we can write in another way also in terms of the effective aperture area. So we can say that a PT here, effective aperture area, then a cross section, and a 4 pi lambda square a S minimum. Okay, so this is about a minimum detectable signal raised to what we can say that we have the term that is about a 1 by 4. Okay, I forgot it. Okay, so this one is about what we can say that a radar equation or a radar range here, and we can consider that the R max is about a maximum range, okay, or a what will be the maximum distance by this given radar there. Okay, this way we can consider here. So this is about a radar range. If you consider that, we supposed to say that what is the minimum detectable signal, that is about one thing we supposed to get here from this, what is the minimum detectable signal, and what will be the operating frequency here of a radar. So already we have discussed that there are the various frequency ranges. Okay, so we supposed to consider that a radar is to be assigned for the different frequency range here, and we have seen that a L band, S band, C band, X band. Okay, so likewise, that is about a 1 to 2 gigahertz, 2 to 4 gigahertz, 4 to 8 gigahertz, 8 to 12 gigahertz, then 12 to 16. Okay, so likewise, so we have the different ranges of the radar here. So this way we can consider here, that is for the radar range. So now we go ahead to the understanding the what is the radar a block diagram here. Okay, so what is exactly a radar block diagrams there, that is to be considered. And this equation will provide you so what will be the requirement in terms of a minimum detectable signal and what will be the requirement in terms of the frequency there. Okay, so means that range always we supposed to consider that it is depending upon the minimum detectable signal as well as the frequency. Okay, so this is about your radar equation now. Next we consider here a radar block diagram. Okay, that is about a overall diagram. Okay, so overall exactly so what components are there in the radar, so that is to be understand here. So that is about a overall block diagram there. Okay, so this one we supposed to be considered here. So for that purpose we supposed to see that, okay, for this purpose we supposed to understand that what will be the requirement for designing the radar. So already we know that the requirement as per the whatever the transmitted power, what will be the received power. Yes. So in that case we supposed to consider what will be the antenna here. But from the transmitter side or if from the receiver side, what are the various components there in the radar? So that is to be understand. So in general, if you consider that we have a transmitter and if we have a receiver. So if I suppose to say that a radar and their block diagram, so I suppose to consider that so it has a transmitter and it has a receiver. But both the devices are connected with a duplexer or a circulator there, and then that is to be connected with the antenna. But exactly what are the basic components in a transmitters available? Okay, just overview of those particular component we will learn here. So that's why we consider that a block diagram of a radar in which we supposed to see that a pulse is to be transmitted by this device here. Okay, so that is about a pulse radar. Okay, this is about a device that will transmit a pulse here. So pulse transmitter. We see here one by one what are the various components of a radar. So this is about your antenna. We supposed to consider that. So then we have the a duplexer here. Okay, duplexer is to be used to differentiate a transmitter and receiver there. Okay, so we supposed to consider that it is block is about a transmitter. So we say that power amplifier. This one is about a requirement for the amplifier. What will the amplified or a power requirement here? And then just like we require a pulse generator or whatever the circuit, we can consider that waveform generator here. And then we supposed to consider that pulse modulator. Okay, this is about a part of a transmitter. Then a antenna used for both the transmitting as well as for the receiving. Then we are able to receive the pulse signal here. So that's why RF pulses we are receiving, that is echo signal. So we supposed to consider that a low noise RF amplifier. Okay. Then we have a mixer. So this is about it. All these are the given direction. Okay. So this one is about a part of a transmitter. Okay. So this one is about pulse modulator. Then we supposed to use mixer here. So mixer we supposed to consider that a local oscillator. Okay, so that we supposed to detect the whichever the signals we are receiving. Then we have the IF. Okay, IF or we can supposed to consider that IF amplifier, and we supposed to consider that a match filter block. Okay, so then we consider the second detector, or we consider that a demodulator. Okay, we have a video amplifier. Okay, video amplifier, and then we have a threshold decision, and then we will get the output here. Okay, so now this one is about your a block diagram. Okay, I hope that you people are able to see here. Okay, this is about your output here. So now we consider here a transmitter block and a receiver block. So this is about a receiver block. So receiver block we have a duplexer, and after that duplexer we'll get the signal from the duplexer to the low noise amplifier. Then we have a mixer. Okay, so likewise. So this is about what we can say that a transmitter. This one is about a transmitter, and this goes to the antenna. So now what will be the a device that is to be useful for the transmitter? So generally we require a large power to be transmitted there. Okay, so that's why we're supposed to use a power amplifier. If we we are using in a X band now, for example, microwave frequency range that are present in our department. Okay, X band components. In that case, we supposed to consider that a klystron or a gun. Okay, because it generates 8 gigahertz of signal frequency there. So we can use a any device that will work at a higher frequency, okay, or for a specific given band of a frequency. So generally, people are using klystron or a traveling wave amplifier, or if it is a small radar, it is made up of a solid state devices. Then we're supposed to consider that a solid state components to be there to generate the a radar signal. So that is about we consider that gun diode, and okay, likewise. So various devices are there; those are used for generating the microwave signal. So we consider here. So what device or what will be the your transmitted signal will be generated, or what will be the device will generate a pulse signal. So that is to be used, and that pulse signal is to be amplified because aim here for the radar we are sending the pulse, and that pulses is to be received. That is echo signal is to be received at a receiver, and then it is to be detected there. So if you see that all other devices, so in that case, if you compare with a klystron or a traveling wave amplifier or a magnetron, so in that case, magnetron is used mostly because it's generating a pulse of a fixed frequency. Okay, so that's why most of the radar they are using a magnetron as a transmitter there. Okay, or a generator. So it generates pulses, then it is to be amplified here. So that's why we're supposed to use a power amplifier there. And before amplifying those particular signal, we're supposed to use here, okay, a waveform generator. Okay, so likewise, so we have the component there, signal is to be generated, and then it is pulse modulated there, okay, and then pulse is to be amplified, and then it is to be a transmitter. So this one is about your a transmitter block. Then we have the antenna. So then that antenna will be of a parabolic reflector because it provides a narrow beam. Okay, so that is about our aim. So this way we supposed to consider that a various component of a radar. That's about a in a radar block. So with this we continue in the next lecture. With this we stop here. So thank you all of you.